Okay, so remind me what's an Eulerian graph? What's an Eulerian graph? Well, those are conditions. What does it mean for a graph to be Eulerian? It has an Eulerian circuit. Okay, but what is that? What does that mean?
The circuit that contains all edges of the graph.
Okay, so it's a circuit, so it doesn't contain any repeated edges, and it contains all the edges in the graph. And no repeated, so that means it contains all the edges exactly once. And as we saw on Tuesday, that in fact a graph contains an Eulerian circuit if that's a question.
All the degrees are
And very important. I mean, and that's very important because that's not going to work. Right, just for an example, here's a graph where all the degrees are even. Okay? But clearly that's not Eulerian. There's no cycle that contains all the edges. So this is the condition that a lot of people forget about because it's just so obvious. The graph must be connected. So contains an Eulerian circuit if all degrees are even and the graph is connected. And so this is Eulerian, but there's something called semi-Eulerian. And we talked about that a bit on Tuesday. So what if I have, well, let's look at an example. Let's look at this graph. Is this graph Eulerian? No, why? We have, how many degrees of 3? 2. Okay, so is there an Eulerian trail? So Eulerian would mean that there's a Eulerian circuit. Semi-Eulerian would mean that there's a Eulerian trail that's not closed. So it doesn't end and start at the same point.
Just to double check, is that a graph contains an Eulerian circuit if and only if all degrees are even?
And it's connected, yes.
Okay.
Yep. Yeah. And it's semi-Eulerian, so what condition can you tell me for semi-Eulerian? It has exactly 2 odd vertices, odd degree vertices, and what's the other condition?
connected.
And connected. Okay, that's important. Okay, so there's an Eulerian trail which goes from the vertex of degree 3. By the way, just to make sure you see it, right? I go down here, and I can go up here, and then I go out here and here. So it contains all the edges, but it starts here and ends here. So it starts at the odd vertex and ends at the odd vertex. What if I put this edge in? Let me make that a different color. What if I put that edge in? Okay, let me ask a question. Is it connected? Mm-hmm. Can you tell me what the degrees are? Mm-hmm. They're all even. Is the graph Eulerian? Yeah, so you can go between a semi-Eulerian graph and an Eulerian graph, either by putting the one edge in between the two odd vertices. By the way, how many odd vertices? What's the relationship between the number of odd vertices in a graph? For any graph, not just Eulerian. You have to have an even number of odd degree vertices. Okay? Okay, so I want you to, I know you've looked at a couple of these problems and you've done the, we talked a little bit about the Hall problem, but I want you to look at, on page 178, 179, and 180, I want you to look at 1, 4, 5, 6, and 8. 1, 4, 5, 6, and 8. Okay, and let me just so if you actually Google problems with Eulerian graphs, there's a problem with monkeys and coconuts. No, I mean, you're on an island with pirates and. Okay, well, Google it. There's all sorts of interesting problems that are related to finding Eulerian circuits in graphs. So, what? Monkeys and coconuts?
What is it?
Eulerian.
Graph?
Mm-hmm. I hope it comes up. I don't know. I didn't check. Okay, so you're working on 1, 4, 5, 6, and 8. Did it come up? All right, maybe it won't come up. And you do know what page this is on. This is on page 170, 78, 79, and 80, I think. Look, I brought a prop today. I forgot that it was one of those fortune tellers. It's too old. Can't read it. Okay, while you're working on that, I'll take the homeworks. Okay, how many of you went, oh, I should have done that on the test.
Oh, yeah, I did.
Thanks.
Pretty much just falls right into the definition.
And I once again, I do apologize. The tests are almost graded. I have to get through the last question. Question number 10? 8? I don't know, whatever the last question was. Not the bipartite question. That was hard enough. The last question. What was the last question on the test?
C4.
Oh yeah, C4. Yeah. Yeah. So just to remind you that if you have a graph on 6 vertices, and I will say that almost everyone got you showed that 5 wasn't enough. Okay, so just in case you can't sleep at night because you're worried about this, here's a graph on 5 vertices. Here's a graph on 5 vertices. Here's the Here's a graph and its complement on 5 vertices. Neither the blue nor the black graph have a C4. So 5's not enough, and 6 is just enough.
It's interesting that you don't have a C3 in either of those graphs.
We don't have a C3 either.
And with 6, you're going to get a C3 and a C4.
You're going to get a C3 and a C4. You're going to get a monochromatic C3 and a monochromatic C4, but they don't have to be in the same graph.
Right.
You just know that either the graph of the complement has a C3 and the graph of the complement has a C4.
So if the error between start and end at the same point, right?但是为了做出来太小。
That's interesting.
4? I'm on. Oh, I'm on number 3. I'm on 4. Are you looking at number 4 yet? Oh, okay. It's a bridge. Is that a cut edge? All the way to some edge.
Oh, what's a bridge?
Yeah.
What's a bridge? What problem is that for?
4.
Oh, okay. It's a
So what's a bridge?
Another way to say cut edge.
It's a cut edge, right? A bridge. Okay, so graph theorists try and use terms that make a whole lot of sense. So here's one graph, and here's another graph. That's a bridge. When I remove that edge, it disconnects the graph. Okay, so it's an edge that disconnects the graph, whose removal disconnects the graph.
Forward error 是有一种解partial differential forward error 他们用计算机解方程式那种，它是一个人，这个人用的可能是100分钟。
地层是有一个，啊有啊，我说错了。
是这样的，因为 forward error 必须要回到原点，所以假设有一个零之一个或者是零知道，它回到原点
不一定啊，你想想它，你想一个8，就是你想这样一个图，
做一个这样的。
这个也是一个 cut vertex， 这也是一个 cut vertex， 但是你还是一个 Euler， 你从这点就这样子。
You know, if you don't talk, I can't hear you.
但我觉得第二个是这个不是 bridge， 就是他刚刚说的。
不是 cutting edge，
但是我觉得，
cutting
因为
edge，
你想，它那个边只能走一次，就回不来了。它如果有个 bridge 的话，它怎么回到另一个？
都一样，
就 bridge。
但是你 Eulerian graph， 每一边你只能走一次，说你想回到原点，除非你有一点。
bridge 的话，它如果再另外再加一个，
对，它不能应该就不是 bridge。
是的，要不然的话你走一次走过去，
就是这样。这应该是不是在？不是吧？我觉得这是你是单边，就单边，它应该不行。
对，我今天我那个
这个意思 Eulerian graph all the which is compact, which is also Eulerian graph.
倾向于
我觉得是它那个点就是基本的，如果它靠这个 edge 的话，它就会把两个点变成 odd， 这样它就不是。
但是我觉得
不是的，不是的。
很多英国的，
可是他想要，
又不是说你看到之后的时候只是。
不是你真正的，它看起来其实不是。
那他的意思是，
他说的是 contain
我也可以
no
看成不
bridge。
行。就是如果它考虑那就等于说是，如果它考 contain bridge，它也不一定是2。看第三题只有5次。
Okay, I'm just going to start on these. So problem number 1, which of these multigraphs? Notice in this, for Eulerian, we don't care whether there's multiple edges. In fact, that often helps us. Which of these are Eulerian, and which of these are semi-Eulerian, which are neither? And in fact, you almost don't even have to look at the graph. You don't have to even try and traverse the graph. The first one, A, neither, because they're all odd degrees. 4 odd degrees, can't be Eulerian, can't be semi-Eulerian. Semi-Eulerian, how many odd degrees would you have? 2. B? Same thing? How many odd degrees do I have? 2. So it's semi-Eulerian, and it must start and end at the 2 different odd degrees. Okay, and we're going to talk about that when we get to problem number 6. What about C? All even. So there's an Eulerian circuit. And D? Now it just becomes a problem to figure out what the degrees are of each of these points. So the degrees are 2 odds. The odd ones are the top one and the bottom one. So it contains an Eulerian trail, and it must start and end at the top one and the bottom one. I don't care which order comes first, and it is connected. Okay? Okay, what about number 4? Can you have any cut vertices in an Eulerian graph?
No.
Are you sure?
You can.
You can have you have one?
Yeah.
Anybody else? You have a cut vertex? Don't show me. Anybody else? Can you have a cut vertex?
Yeah.
Are you sure? I'm just. So yeah. There's what's the conditions I need for an Eulerian graph? Connected. Use each edge once, no, but what condition in particular tells us that it's Eulerian? We don't have to find the Eulerian cycle. All the degrees are even. Okay, so you can have a cut vertex. Can you have a cut edge? Okay, so who's going to help me figure out, can you have a cut edge? Let's see, if this was Eulerian, then what can you tell me about, if that graph over there, the dumbbell, if the dumbbell was Eulerian, then what could you tell me about all the degrees? They're all even, okay? All even degrees. So there'd be some even degrees over here and some even degrees over here. This would have even degree and this would have even degree. What happens when I remove this edge? Well, let's talk about this bubble over here. With that edge in, it had all even degrees. Now, with that edge removed, what are the degrees here? Here. Well, all of them are odd? One is odd. And what about all the other ones? Yeah, but I'm just looking at this bubble. Okay, let me go back again. When I had that edge in, all the degrees are, this is Eulerian, if this is Eulerian. All the degrees in this graph are even. All the degrees are even. Okay, so now, all the degrees were even. Now, tell me the parity of this degree? Odd. Now, let's just look at this bubble. This bubble right here. Before I removed that edge, all the degrees were even. Now, when I remove that edge, I have all even and what? Oh, is that okay? Okay, what you said was, in this bubble, I now have all even and one odd degree. No? Is that okay? Why not?
Because it could be a standalone graph.
It can't be well, it is, there it is, bubble.
Yeah,
It is.
but it isn't. So
It can't be, because
the sum of the degrees is odd.
the sum of the degrees, I have I have all even degrees except for one, all even plus even, plus an odd, then the sum of the degrees would be odd. Sum of degrees would be odd if I remove that edge, so they can't be a bridge. Okay? Okay, is that proof clear? It's a pretty neat proof. Okay. I have no idea where that was. Oh yeah, that was, I made that one up. No, that's II. If G is an Eulerian graph, then G contains no bridges. So if it was Eulerian, all even degrees, and it contained a bridge, then we'd be in trouble. So in fact, an Eulerian graph contains no bridges. Okay, III. Eulerian graph of odd order. G complement is connected, then G complement is also an Eulerian graph. Make sure we got that right. G is an Eulerian graph of, this is the important part, of odd order. G is an Eulerian graph of odd order. So remind me, what is the complement? So here's G. G, it's Eulerian of odd order. Odd order. N is odd. So what can you tell me about the degrees of all the vertices here? All the degrees are even. Okay. Now, what I know is that G complement, here's G complement, it contains all the edges that aren't here. All the edges that aren't here are in here. So I'm just going to pick a point in general. Here's a point V, and here's the same point V. In G, the degree of V is what? Is even. In G complement, the degree of V is n minus 1 minus the degree of V. Okay, where'd the n minus 1 come from? Well, So when I put the complement, when I put G complement on top of G, all the edges between all the vertices are there. Every vertex has degree n minus 1, okay, which is n minus 1 is, oh, sorry, yeah, n minus 1 is even, yeah. So n minus 1 is even, so this is an even number minus an even number. So it's even. Every vertex here has even degree, and we're told that G is connected. That G complement is connected. So if this is a Eulerian graph, and its complement is connected, and the degree matches of odd order, and the degree here is every vertex has even degree, then this is also an Eulerian graph. Okay? The key here is that it was connected. Again, G is an Eulerian graph of odd order. G complement is connected. Then G complement is connected. Then G, by the way, how do I know that G is connected? Because what? It's Eulerian. That's part of the condition. So I know that G is connected. We're told that G complement is connected, so G complement is also Eulerian. Okay? Again, this is just a sum of two numbers. Sum of the degree in G plus the degree in G complement. Okay. Okay, which KPQ, what is KPQ? KPQ. KPQ. It's hard to decide if it's Eulerian if we don't know what it is. Come on, I know you know.
No, it's like two graph and one is with P orders and one is with Q orders.
Okay, so I have P vertices and Q vertices, and what does the K mean?
It's complete.
It's complete. Now, it's not a complete graph, right? Because these are all independent. Okay. So let me ask you, when is KPQ, forget the semi, Eulerian? What can you tell me? What by the way, let me sort of feed it to you. What's the degree of every point here? In just KPQ. What's the degree of every point here?
Q.
And what's the
P.
Q? Every point here has degree P. So what would make this Eulerian if both are even? If P and Q are even, notice it's connected, of course. We're not allowing 0. I know 0 is an even number, but that doesn't count. So P and Q are positive, even numbers, then in fact this would be Eulerian. Okay? We want to know, when is it, we do, don't we? When is it semi-Eulerian? For which P and Q, P greater than or equal to Q greater than or equal to 1, are they semi-Eulerian? So one more time. The degree of all these vertices? P. The degree of all these vertices? Q. How many odd vertices do you have to have in a, how many odd vertices can you have? How many odd vertices must you have in a semi-Eulerian graph? 2. So we can only have 2 odd vertices. Now, how many vertices are up here? And they all have the same degree. How many vertices are here? And they all have the same degree. Okay, so what can you tell me? If I have a chance of having a semi-Eulerian graph, what can you tell me the size of one of these must be? 2. Is that clear? Because I can only have 2 odd vertices. Okay, so one of the sets, let's say Q, has 2 vertices in it. Now it's semi-Eulerian, so that means there is no Eulerian cycle, no Eulerian circuit. By the way, if this is a complete bipartite graph, I don't care how big Q is, okay, let's say, I don't care how big P is, what's the degree of each of these points? 2. And that's even. Okay, so they all have the even degree. So what can you tell me about when does this graph have exactly 2 vertices of odd degree? When P is odd. So K 2P is semi-Eulerian when P is odd. Okay? And that's if and only if. If P is not odd, then what's the degree of these points? If P is even, let me make it even easier. If P is even, then what's the degree of these 2 points?
It's even.
Even. And the degree of these 2 points?
2.
Sorry, these P points?
2.
2, which is also even. And is it connected? So it's Eulerian. Okay? Questions? Okay, now problem number 6. Problem 6, he's gonna sort of show you the connection between Eulerian and semi-Eulerian. So the following multigraph is semi-Eulerian. How do we know it's semi-Eulerian? There's 2 odd vertices. And what's important is, don't ever be tricked. This is connected. You should always, I mean, it looks plenty connected, but you know, sometimes I slip one in and I may make it look connected, but just watch carefully. It's like a sleight of hands. Okay, so this is certainly connected, and it contains 2 odd vertices. What are the 2 odd vertices? 1, 2, 3, 5, 6. Which ones? X and Z. X and Z are 2 odd vertices. Everybody else you should check has even degree. Okay, form a new multigraph by adding the edge X to Z. You don't have to do that. What happens when I do? Then the degree of X and the degree of Z become even. Everybody else is still even. The graph is connected. So the resulting graph is Eulerian. And if you find an Eulerian circuit, then somewhere on that Eulerian circuit is the edge. One more time. An Eulerian circuit is a circuit that contains every edge. Then one of the edges on the Eulerian circuit is going to be XZ. So if I take the Eulerian circuit and I remove the edge XZ, then the result is an Eulerian trail that starts at X and ends at Z. Okay, so there's this relationship between semi-Eulerian and Eulerian graphs. Okay, if I have a semi-Eulerian graph, I can make it Eulerian by adding one edge. If I have a Eulerian graph, I can remove one edge and make it semi-Eulerian, and I know exactly where it must start and end. Okay? Okay, one more time. For, number 8. Did I get all of that? Yeah, okay. So number 8. You started looking at number 8. So this is sort of, it's not a deep application, but it's an application of Eulerian graphs. So you imagine this, and you know, again, if you, I think this is the museum problem. You go to a museum and you want to go through all the doors in the museum. And you want to go through all the doors efficiently. And when I say efficiently, it means that you probably don't want to go through any door more than once. And you'd like to go through every door exactly once. Okay, so if I take this floor plan, and both of these floor plans, and I put a vertex in the middle of each room, I'm not going to draw the graph. But you can tell me, if I were to draw an edge between any 2 rooms that are connected by a doorway, then you can tell me what the degrees are of each room. Yep? And just, there's no small doors. That little gap in B, it's not like a secret door. Okay, so what can you tell me? Can you start? Primarily, we're outside the museum. We're by the Blue Bear. And we want to walk into, I guess that's the convention center. We want to traverse each door exactly once. And we want to be able to come out back outside. Can we do it for A? Yeah, the degrees, we would form a graph. Right? Every room has a vertex, and every door corresponds to an edge. And the degrees would be, I'm going to read off my degrees. 2, 4, 2, 2, 2, 4, 4, 2, 2, 2, 2. Those all sounded even to me. So in fact, I don't even have to tell you what the Eulerian trail is. I know that I can go through each door exactly once and start where I ended, or end where I started. Okay, what about for B? B?
I feel like that little gap does need to be a door.
Well, that's cheating.
Well, but I mean, then you still don't use, there's still no path from A to B, even with that little gap as a door. But then the second part of the question where it says which door should be closed to ensure the existence of such a route, I feel like to be able to do it in one door, we need that door to be open.
Yeah, I mean, I don't know the authors, but I just, if we can, looking at the graph, assuming that that's not a door, then there's a room that has 3 doors and a room that has 5 doors.
Right.
Okay, and then we would not be able to get from A to B, which is the problem that he's offered for us. Okay, so again, there are problems like this that you can find if you like to play with these things. There's lots of problems for Eulerian graphs and Eulerian types of graphs. And they're fun, but that's about it. I want to look at so remind me, does he use times, does he use PM cross PM?
For Cartesian
For
product,
Cartesian
it's a
product?
little square.
He uses square, yeah, I know. That's the new thing. I'm an old guy. Okay, by the way, I think, did I put on Canvas the talk I'm giving next Wednesday? Okay. If you want to, just let me take 2 minutes. So Paul Erdős was probably the most prolific mathematician, more than Gauss, more than Pascal. I mean, he wrote over 1,500 papers, and there's a claim that he didn't have a home. He lived in a communist country. He had an apartment. It had his name on it, but he wasn't there much. He traveled around the world going from mathematician to mathematician, and I was fortunate enough to be able to spend several visits with him. He would come and visit, and I'm going to tell you a little bit about his life. If you want some information, you might want to look up. I'm not saying you have to come or want to come, but you might want to look up the Erdős number. Okay, I mean, you'll get many hits, and you'll get a lot of information about the Erdős number. And I'll tell you a little bit more about the Erdős number. And depending on how long it goes, I may tell you about some other things about Paul that are not necessarily mathematical in nature. Okay? All right, so that's next Wednesday at 6:30. Yep, I don't know. That's next Wednesday at 6:30. Yep. And there'll be food. If that helps. Okay? And it's about graph theory. It's something that you might want to find out a little bit more about one of the premier graph theorists of our times, at least of my time, maybe not your time. Okay. So I want to move away from Eulerian graphs. It's either there's nothing to do for an Eulerian graph. There's two conditions. I want to find out whether an Eulerian graph is connected, and if it has all even degrees, connected in all even degrees, then there's an Eulerian circuit. And if it has all even degrees except for 2, then it has an Eulerian trail, starts and ends at the 2 odd points. So it's not very interesting, depending on your view of things. Okay. So I forgot that this was one of those fortune-telling cubes, but so this is an icosahedron. So if you look at page 201, if you look at page 202, there's a picture of this. Oh, this isn't. No, I didn't bring the right one. Okay, this is a 20-sided. Okay, the icosahedron has all sides are pentagons, and it's 20-sided. And Hamilton came up with this game. Now, I don't know. No one seems to have an original, and I don't know if this is an original on page 201. So the idea was that this was supposed to be the world, and there was a peg at each point, and you were supposed to visit each of the cities exactly once and get home. Okay? So you don't have to go through every path exactly once. You want to visit each city exactly once. And there were variations of it, and this is later in the early 1900s, they came out with this two-dimensional version of the three-dimensional game. Okay, so Hamilton produced what people believe is a three-dimensional version of it, and there are many different variants of how you can play the game. And again, when you see the three-dimensional version of it, he actually tried to be accurate where each of the vertices corresponded to an approximate place of the city, of a city in the world. Okay, so you could visit city after city, and then make your way, visit each city exactly once. Visit each city exactly once, and then get back to the start. Okay, so it gives you an answer here. So here is the icosahedron on page 202. Here's the graph that results. Okay, so you have this three-dimensional object, and then the graph is C on the top of page 202. And now the question is, of course, the question is, is there a spanning cycle? Is there a Hamilton cycle? Of course, we don't know Hamilton yet, because he's the creator of this. We haven't named it after him yet. But is there a cycle that visits each city exactly once and gets back to the start? Okay, so it sounds the same. Rather than traversing each edge, we have to visit each city. So if you look at 5.1.2, 5.1.2, we see they give us a Hamiltonian cycle, a spanning cycle. Spanning means all the vertices are contained in it. It's a cycle. It starts at a point, it ends at the same point, and it contains all the vertices in the graph. Okay, so, and there are many of them. There are many of them, and you might want to find different ones. So this idea of Eulerian graphs, if you remember, Euler was provided the Königsberg bridge problem in the late 1700s, 1780s. So Königsberg wants to know the answer, traversing each of these bridges, and Euler comes up with the answer that it has to be connected, and every vertex has to be of even degree. He doesn't use the word vertex, he doesn't use the word degree, none of these words exist yet. That doesn't really come until the late 1800s. So the idea of Hamilton is similar. I don't want to traverse every edge, I want to visit every vertex. How much harder can that be? And is there a condition, all even degrees, is there a condition that tells us when a graph is Hamiltonian? Okay, so I want you to look at problem 5.1.2. So again, it's a spanning cycle. So it's a cycle that contains all the vertices, is a Hamiltonian cycle. Okay, so part A, is every cycle Hamiltonian?
Yes. Or n squared 3 or equal to 3.
What was that?
So like Cn.
Cn,
As
yeah.
long as n is 3 or more, then yes.
As long as, yeah, C2 doesn't,
Oh.
we don't like C2. No, I mean, even, yeah, we're going to have no multiple edges. So C3, as long as it's, well, of course, I mean, this is a cycle. Here's a C4. So I start, there's not much choice, and then once I leave a vertex, there's only one other choice to go, and as long as it's a cycle, we're able to get back to the start. Okay, so that one's pretty simple. So what's the smallest number of edges in a Hamiltonian, in a graph that contains a Hamiltonian cycle? Graph of order n is Hamiltonian. What is the least, on my part, II, what is the least number of edges in the graph? It could be a trick question, but it's really not.
N.
N. Well, if it's got a cycle that contains all the vertices, then and it's got n vertices in it, then it better have at least n edges. Okay, and that's the minimum. Just take a cycle. Take C5, take C6, C7, and so forth. Okay. I'll ask. Is Kn Hamiltonian? Yeah, that's pretty clear. Right? It's almost you can do anything. Start at any vertex, go to another vertex, and you always have another vertex to go to. So that's pretty simple. What about KPQ? Oh, what is KPQ? Oh yeah, there it is. Lucky. Okay, so is KPQ Hamiltonian? What was that?
P equal Q.
If P is equal to Q, if P is equal to Q, then I start in P, and I simply go, well, let's label them. 1, 2, 3, P, and P is equal to Q. So this is, I'll use a different color. Hopefully red works. 1, 2, 3, P. So P is equal to Q, then I have the same number of vertices at each point. So I'll go 1 to 1, to 2 to 2, to 3 to 3, to 4 to 4, to 5 to 5, to P, and then back to 1. Okay. So one more condition. It's a tricky condition. KPQ is Hamiltonian. If P equals Q, and it's at least 2. K11 is not Hamiltonian. Okay. Okay, well, now take a minute. Which of the following graphs in 5.1.3 are Hamiltonian? This won't be a minute. Maybe it'll take more than a minute.
cycle，
然后还有这个 path，spanning 的意思是什么？
spanning 就是 contain 所有它原graph 的所有点。
这个图用的很复杂。
就是
path 不能按这个复数，不能比 vertex 数，不是 C，所以 B 不是 A 是。
可以等一下，我上去这样走，这样走，这个走，这个走，这是多少？
不行。我只要倾销两下就行，是。
你到这儿之后就这样，然后你过来，
那条件到底是什么呢？
你是完全一个对称
我说
的。
你下面的只要我们都知道它都是一的，那就一定可以。然后前面那个我没听懂，你快给我讲一下之前那个题。
说这个图形它就是一个，就比如对于的关中心那点。
来，学法看一遍。
哪个题啊？
就是刚才讲的那个画画的那个，
但它可能得要归
刚才讲的那个是个啥什么？题目啥？那个判断就是
之前是课本也是数学家们研究透彻，他们也会研究。我们要相信数学家。
今天选这个。
Oh, this is a lot harder than Eulerian, huh? Anybody find any, I call them tricks, but we don't like tricks. Anybody find any important properties without reading ahead?
但是因为它是就是一
Okay, so let me go back. How about, did anybody find any Hamiltonian cycles for A? A's easy. A's pretty simple. So unfortunately it doesn't label the vertices, but if we go up we start on one side, we go up and then down to the middle, go through those 3 points up to, and then down and around to the bottom, we're in good shape. Well, it looks almost the same as B. Right? It almost looks the same. Anybody find a Hamiltonian cycle there? Okay, so let's look at, and unfortunately, unlike Eulerian graphs, there's no nice way. We'll see. If you throw enough edges, if the graph has enough edges, then it'll be Hamiltonian. But there's no standard nice way to look at a graph and go, yep, it's Hamiltonian. I added up all the edges, or I added up all the degrees, or I did something. So you have to use maybe ad hoc techniques. So let's just sticking with this graph. So if it's Hamiltonian and I have a vertex of degree 2, then what can you tell me must be the case? If it's Hamiltonian and I have a vertex of degree 2, so if this is Hamiltonian and I have many vertices of degree 2, what can you tell me about those edges? Okay, so these edges, this edge and this, if it's Hamiltonian, that edge and that edge must be on the Hamiltonian cycle. Is that clear? There's no other way. We're stuck. We go into this vertex, out of that vertex. There's no other way to get in around. Okay, what about this vertex? Well, the same thing. And what about this vertex? And what about this vertex? And now we're done. Well, kind of. There's no way I can have one cycle that contains all the vertices exactly once. Because if I had a cycle that contained these vertices of degree 2, then I would have to use these 8 edges, and there would be no way that I could pick these 2 vertices up. Is that clear? So in fact, one of the things that you might look for is vertices of degree 2. Let's actually limit it some more. The graph, if you have a chance of having a Hamilton cycle, a cycle that contains all the vertices, then in fact you have to have, it has to be connected, has to have degree at least 2. Right? Has to be connected, have to have degree at least 2. And in this case, if I look at all the vertices of degree 2, we must be able to, in fact, be able to cover all the vertices, or at least not use all the vertices, not use all the vertices in the graph. So here are 4 vertices of degree 2, which gives me a 10 cycle and not allowing me to have a 12 cycle. Okay, so there's no 12 cycle. By the way, there is 11 cycle. Okay, but I don't want an 11 cycle, I want a 12 cycle. Okay, questions? Okay, what about A? What about A? Anybody find the Hamiltonian cycle in A? I'm still on page 203. Yeah? Okay, so I'll assume you all can find the Hamiltonian cycle. And C? So let's see. I'll just, we have a vertex of degree 2. We have another vertex of degree 2. Oh, but I only have 2 vertices of degree 2. So of course, if I know that I have 2 vertices of degree 2, I know that I have to use those 4 edges. Okay, so I'm going to use, one more time, on 5.1.3c, the top vertex has degree 2, and this vertex on the right side has degree 2, so I have to use those 4 edges. If I have to use those 4 edges, then I'm stuck. It forces me into using other edges that will force it to not be Hamiltonian. Okay? So you can actually try and convince yourself that this graph is not Hamiltonian. Okay, I want to look at one more. Actually, I want to look at 2 more. 2 more problems. So I want to jump to page 208. So we're gonna start to look at one more time, unlike Eulerian graphs, there are no set conditions that always tells me that a graph is Hamiltonian. Other than if there is a cycle that goes through all the points, then the graph is Hamiltonian. That's like cheating. Okay, there's no nice conditions that for any graph you look at these conditions, the graph is Hamiltonian. There are conditions that imply that it's Hamiltonian, but in fact they're pretty restrictive, as we're going to see. But let's look at 5.2.1. Okay, don't read anything yet. Let's just look at 5.2.1 and see if you can find a Hamiltonian cycle. It only has 6 vertices. So you just maybe I'll label them for you. Not for any reason. I'll label it A and B and 1, 2, 3, 4. 6 vertices. There's got to be a 6th cycle there. Okay, I'm going to say it again. There's only 6 vertices. Either there is a 6th cycle or there isn't. All right, let me stop you for a minute. Okay, is it Eulerian? It's not Eulerian. Why not? There's what? There's 2 vertices of degree 3. Oh, is it semi-Eulerian? Yeah, it's clearly connected. Like that, you can tell whether it's Eulerian. You can tell whether it's semi-Eulerian. I mean, immediately, just by looking at the degrees of each vertex. Why isn't Hamiltonian? Why isn't a spanning cycle just as easy? Okay, so there's a reason I'm looking at this graph here. So I want to look at the top 2 vertices. Look at the top 2 vertices, and I throw all those edges away. I throw all the edges on the top 2 vertices away. So what's left is this. Right? What's left is this graph. Now, if there was a Hamilton cycle, then let's say I would be able to go this, so there would be 4 edges. 4 edges out of those 2 vertices, and those 2 vertices are adjacent to everything. So there would be 4 edges out of those 2 vertices going to how many pieces? Going to how many pieces? I don't want to count them for you again. Going to 3 pieces. And I have to start and end. So maybe these 2 go to this one, and this goes here, and this goes here. And now there's a problem. I can't get from here to here. So what we're going to see is, we're going to look at this idea of disconnecting sets. So sets that disconnect. So here's a set of size 2 that disconnects the graph into 3 pieces. If we have a set of size, if I have a set of size S, and I break it into more than S pieces, then the graph is not Hamiltonian. And that's where we'll start. We'll start with that on, what's today? Tuesday? We'll start on that next Tuesday. And I will have your test graded. I will have the homework graded. I know I've been bad. I just, okay, so just to give you some things to work on, because I know you just love this stuff. Okay, so there's problems on page 210, 211. So one of the questions is, what values of M and N is the product PM, PN Hamiltonian? So we went through KPQ. KPQ is Hamiltonian if and only if P is equal to Q is greater than or equal to 2. Mm-hmm. When is PM cross PN? You remember what this is, and there's lots of pictures if you turn to page 211. Here are some, here's a 3x3, 3x4, 3x5, 3x6. Oh, maybe there's something with 3s. Okay. If you want a real challenge, you might want to look at G. If you just can't stay away from F on page 211. The ones on page 210, just, you need something to do while you're working this weekend. Just as a leisure exercise, you might want to look at the problems on page 210. Okay? Questions? Have a nice weekend.